Okay guys, so now we're going to review chapter 7. This was a tricky chapter for a lot of people. So hopefully as we go through this, maybe it will clarify some of the things that you've been wondering about from this chapter. So this chapter was about covalent compounds, and one of the really important things that you need to do from this chapter is you need to be able to draw Lewis structures and figure stuff out from the Lewis structures. So this question is asking me how many single bonds are present in the Lewis structure of CO2. So there's a process for drawing a Lewis structure. Remember, the first thing you need to do is look up the number of valence electrons in the atoms in the structure. So carbon is in the 1, 2, 3, 4th column, so it has 4 valence electrons, and then oxygen is going to have 6. So since I have 1 carbon and 2 oxygens, that means I have 16 valence electrons to work with. So the first thing I want to do, and I should probably be doing this in pencil. Let's see if I have a pencil here. I don't have a pencil, but you should do this in pencil. You're going to draw kind of a skeleton structure and just put single bonds between all of the elements. And then you want to put the first element in the middle, unless it's hydrogen, and then everything else on the outside. So now I've used 1, 2, 3, 4 of my electrons, because remember each bond has 2 electrons. So 1, 2, 3, 4. Now I need to count up to 16, and I put the electrons around the outer atoms first. That's very important. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so now I need to ask myself, do all of my atoms have an octet? So if I look at my oxygens, they have 1, 2, 3, 4, 5, 6, 7, 8, because they get to count the electrons from the bonds. So this oxygen is good. This one has the same number, so it's good. But carbon only has 4 electrons right now, and it needs an octet. It needs to have 8. So what I need to do is I need to take this lone pair, remember 2 electrons is a lone pair, and I need to make it into a double bond over here. And if I do that, then I'll have 6 electrons around carbon. So that means to get 8, I need to do the same thing with that lone pair. And when I do that, my carbon dioxide molecule is going to end up looking like this. And you'll notice everything has an octet now. My oxygen, even though I shared that lone pair, it still has 8 because it's got 1, 2, 3, 4, 5, 6, 7, 8. And carbon also has 8. Now the question here actually was how many single bonds are present in the Lewis structure, and there's double bonds. These are both double bonds, so there's no single bonds. So the answer to that question would be 0. No single bonds there. No lone pairs on the center atom. There's some lone pairs on the outer atoms, but not on the center atom. Okay, you also need to be able to draw a Lewis structure and figure out the shape of the molecule that you draw. So let's draw CH4. Carbon, we already looked up, has 4 valence electrons, and hydrogen is in the very first column, so it's just got 1, but there's 4 hydrogens, so I need to add 1 4 times, so I have 8 electrons to work with. And if I take my carbon and put my 4 hydrogens around it, that gives me 1, 2, 3, 4, 5, 6, 7, 8. So I've actually already used all my valence electrons. And hydrogen doesn't need an octet. Hydrogen only needs 2 electrons. That's important to remember. So 1, 2, this hydrogen has 2. And then carbon, you'll notice, has an octet because it has 1, 2, 3, 4, 5, 6, 7, 8. So this structure is done. This is the structure of methane. Now you do need to remember the shapes. So there's only 5. If you've got 4 atoms around your central atom, it's tetrahedral. And I'll just draw a couple of other shapes just to remind you. If you have something like this, where you have 3 atoms bonded to your center atom and a lone pair, that is trigonal pyramidal or pyramidal. If you have 3 things bonded, but there is no lone pair on your center atom. You might have some lone pairs somewhere else, like these, but none on the center atom. This is carbonate ion. This shape is trigonal planar, so it's flat. This one's three-dimensional. Trigonal pyramidal is three-dimensional. Trigonal planar is flat. And then the carbon dioxide that we just drew up there would be linear because it's got two atoms and no lone pairs on the center atom. And then lastly, if you have something like water, that shape is called bent. Okay, so those are your 5 options for shape. I think people got pretty good at shape in chapter 7. Okay, and you need to know a little bit about polarity. So for a bond to be polar, it needs to have a negative side and a positive side. And the negative side is going to be the side with the more electronegative atom. And then the positive side would be the less electronegative atom. Okay. I don't know if you can hear that. They're like mowing my lawn out there or something. So it's a little bit loud. Sorry about that. So if you look on the periodic table, the more electronegative elements are over here on the right side, with fluorine being the most electronegative, and then less electronegative elements are over here. So the more distance there is on the periodic table between elements, the more polar a bond will be between them. So for example, if you compare a bond between C and N and a bond between C and O would be more polar because there's more of a difference in electronegativity. So the oxygen is going to be able to hug the electrons better, pull them to itself better than nitrogen. So just want to write down like CO is more polar. Oh, sorry. Okay, more polar than CN. Okay, we also need to talk about hydrogen bonding really quick. So for hydrogen bonding to happen, you need to have hydrogen, and it has to be bonded to one of 3 elements. So you have to have either HF, HO, or HN. Okay, and those are the only things that will do hydrogen bonding. If hydrogen is bonded to anything else, it's not going to do hydrogen bonding. Okay. Last thing we need to talk about are these heating curves. So to understand these heating curves, you need to understand some stuff about phases on the heating curves. So right here on the heating curve, this diagonal part right here is where your substance is a solid. This diagonal part is where your substance is a liquid, and right here it's a gas. And then on these flat parts, these are where phase changes are happening. So this would be like melting, or if you're going in the opposite direction, it'd be freezing. And then this would be like boiling or evaporating, or if you're going in the opposite direction, it would be condensing. So you need to understand that, and then you need to just be able to answer questions from the graphs, which can be tricky. So let's look at this one. How much energy must be removed to freeze all of the liquid if it starts at 60 degrees Celsius? So it's talking about 60 degrees Celsius. So you want to make sure you're looking at 60 on the right axis, because if you're like me, you see 60 and you want to go straight to the x-axis. But that's not degrees Celsius, that's kilojoules. So we're going over here. So 60 degrees Celsius is like right here. And it wants to know how much energy has to be removed to freeze. So it's like all of it's a liquid right here. At this point, it's all frozen into a solid. So it's basically just asking me what is the energy between here and here. And energy is on the x-axis. And this is about 30, and this is about 10, maybe a little bit less than 10. So it's going to be about 20, maybe like 22. To freeze or melt. To freeze, you would have to remove 20 kilojoules. To melt, you would have to add 20 kilojoules, because 30 minus 10 is 20. Okay, so that's kind of some basic stuff for chapter 7. I know that was a little bit longer than the other chapters, but it's an important chapter to understand. So, good luck. Let me know if you have questions.